All right, in this video, we're going to talk about blood pressure and factors that affect blood pressure, so arterial blood pressure. And we know by solving Purcell's law for blood pressure, right? So Purcell's law is always Q equals delta P over R. If we fill in the parameters for the entire cardiovascular system, then Q becomes cardiac output, delta P becomes blood pressure, right? That's the driving pressure for flow through the vascular circuits. And resistance would become total peripheral resistance. So if we solve this for blood pressure, right, we get blood pressure equals cardiac output times total peripheral resistance. And remember, total peripheral resistance is just the resistance of all blood vessels, which again is really hard to compute. It's usually you solve for, you plug in everything else and solve for that. You can't really calculate it on its own. But again, we can regulate either cardiac output and or total peripheral resistance to alter blood pressure. Now, having said that, we talked a lot about regulating cardiac output already. We're going to talk a little bit about, when we get to the vascular sections, the hemodynamic section, we'll talk about controlling total peripheral resistance a bit more. But there are actually a couple other factors that will sort of feed into this, some of which we've already seen. Okay, so, but let's go over to our image on the left here, right? And so blood pressure in the arterial circuit, right? So in here is directly proportional to the volume there, right? The volume in that arterial circuit at any given instant. And here's the easy analogy, right? The pressure in a balloon is proportional to the volume of air in that balloon, right? The more air you push into that balloon, the more air you push into it, the higher the pressure on the inside will be. And yes, it also depends upon the elasticity of the balloon. And so we could get into the compliance or the inverse of that, the elastance of the arterial circuit. And that does play a factor. But for the moment, we'll leave that out, right? It's largely, and it is proportional to the volume in the arterial circuit at any given instant. Now, at a given instant, how much volume is in the arteries is determined by the sort of the ratio of the input to the output, right? And so the input is entirely cardiac output, right? Whereas the output is determined by, as I have it here, the tension of the smooth muscle in the vascular circuits, right? And I like to call that runoff, right? So the output rate is our runoff rate, and that can be adjusted by adjusting the resistance of that vascular smooth muscle, right? And so at a given instant, right, if cardiac output is higher than the runoff rate, in other words, we're putting blood into the circuit faster than we're letting it out of the circuit, then volume would rise and blood pressure would rise, right? However, conversely, if runoff were greater at a given instant and output were lower, right, then of course blood volume would fall, right? We're letting it out faster than we're putting it in. Blood volume would fall and then blood pressure would fall, right? Well, that is exactly the scenario we see during a given cardiac cycle. So if we come down here, we look at our single cardiac cycle, or maybe a little bit more than one cardiac cycle, we see our arterial pressure falling, right? And then the heart contracts and ejects blood, right? Our stroke volume, and as it ejects blood, the pressure will rise, right, up to the peak, which gives us our systolic pressure, right? And during that phase, cardiac output is higher than runoff, and so pressure is rising, right? Cardiac output greater than runoff, and I actually have that down here. Arterial input is greater than output. Now, as our pressure begins to fall, right, there's a point at which the output right? Our pressure is falling. If our pressure is falling, then the runoff is starting to exceed our filling of that arterial circuit, right? And so in that phase, runoff, right, is greater than cardiac output, and pressure is falling. Okay? So, and there's a reason. You might say, well, what about this little section right here, right? If pressure's falling right here, why is this still considered cardiac output is greater than runoff? And it is, even though the pressure's falling, that's because of the inertia of blood leaving the ventricle as it's ejected. So we'll get flow even when pressure's not favoring it necessarily, because there's a kinetic component to the blood movement, right? You can't stop the blood from moving instantaneously. But anyway, so what we're seeing just during a single cardiac cycle is this sort of rising pressure when input exceeds output, and then falling pressure when output, runoff, exceeds input, cardiac output. All right, well, that's during a single cycle. Now, let's think about blood pressure overall, right? And oh, by the way, we do have our diastolic pressure on here as well. I'm going to point that out, right? Which means, of course, we also have our pulse pressure, which would be the difference between the two, just pointing out what else this graphic shows us. Okay? Finally, we could look at our mean or calculate our mean blood pressure from this, right? Which equals, I should make a point about this, right? Mean arterial pressure. You might think that mean arterial pressure would just be the average of systolic and diastolic, right? That's not actually true. It would make sense, but it's not true. And then here's the actual equation. So it's 1/3. So you could sort of do 1/3 times the pulse pressure plus the diastolic pressure. So basically what it's saying is it's 1/3 of the way up from the diastolic pressure. It's not in the middle. It's not halfway up to the systolic pressure. And the rationale for that is that the heart spends more time in diastole than systole. And so that drags it. So in other words, you'd have to integrate this over time. That drags the mean pressure over time closer to the diastolic pressure, just because it spends more time at lower pressures than it does at higher pressures, right? So it's instead of it being half of pulse pressure, it's 1/3. And that gives you a pretty good estimate of the mean over time, mean arterial pressure. Okay, let's come back to our Poiseuille equation up here that we solved for blood pressure. And of course, we can see that cardiac output and total peripheral resistance, which we already talked about, is due to vasoconstriction or vasodilation of these vascular beds, right? Sorry, the R here is runoff, but runoff is determined by R resistance, right? Total peripheral resistance of those vessels. But it's a little bit more complicated than that. There are a couple other things that factor into the regulation of blood pressure over time. And we've already seen these, right? And so what I'm going to do is I'm going to add a simple factor here that we've seen, and that is, or heard of, central venous pressure, right? Central venous pressure is one of those factors that can be regulated to adjust cardiac output, right? We've already seen this. We can put this in here, right? How about we put in inotropes, right? They're generally positive inotropes, right? Epinephrine, norepinephrine are positive inotropes that can change contractility of the heart and change cardiac output by increasing stroke volume. We've seen this before. We've seen some of what I'm about to show you too, but the other two factors that play into adjusting cardiac output and therefore blood pressure are central venous pressure and blood volume. Those are, and again, the reason I'm pointing to these specifically is because these are the ones that are regulated, right, to adjust cardiac output, right? They are factors that are sort of adjusted over time to adjust cardiac output and blood pressure. Well, let's list them all and then we'll talk about each one. So we've got blood volume. We've got potential for, even though reasonably rare, venoconstriction. Right? Now remember, up here it was vasoconstriction. Or vasodilation. right? Veno refers to veins, vaso referring to the arteries and arterioles that are affecting our total peripheral resistance. Venoconstriction is on the other end of the circuit. It's at the venous end of the circuit, okay? And then the last one we'll put in here, again, because we've seen it before, is the muscular pump, right? That's the skeletal muscles contracting to compress the veins that pass through them, squishing that blood back into the central veins and increasing the pressure there, right? And so I should put arrows on these, increasing blood volume increases central venous pressure. Venoconstriction increases central venous pressure. Muscular pump increases central venous pressure, which of course increases cardiac output, which of course would increase blood pressure, right? And of course we could go the opposite direction with all these. Remove the muscular pump, remove the venoconstriction, decrease blood volume, right? And then all these arrows go the opposite direction. Okay? Now, how are these things affected? Well, the muscular pump is a physical factor, right? That's not, we don't need to, there's no other component of it, right? Increasing blood volume, right? So we can do two things. We can increase intake, or we could decrease output, right? So in other words, you could drink more, right? Or you could decrease your output by decreasing urinary losses, right? And those things over time, and we could have other modes of input if you like. We could give you an IV, right, which would increase blood volume much more rapidly than a lot of other mechanisms. And of course, that extra volume ends up in the venous circuit because of its high compliance, which despite that high compliance does increase our central venous pressure a little bit, favoring blood flow back into the heart, right, driving our venous return. So this central venous pressure, this arrow towards cardiac output, I can slide it in here, would be increased heart filling, right? Again, increasing preload, which leads us to the Frank-Starling mechanism, which leads us to an increase in stroke volume and therefore cardiac output, right? So our increased blood volume increases heart filling. Venoconstriction does the same thing through a different mechanism, increases central venous pressure, increases heart filling to increase stroke volume and cardiac output, and as does our muscular pump, which not by constricting the veins, but by pushing more blood into the veins from the skeletal muscles that are contracting. All right, and there you have it. Now, when we get to renal, what we'll do is we'll talk about the factors that affect, largely, this intake and output, right? And renal will be the output. But we certainly want to make sure that during this section, we understand the mechanisms that affect venoconstriction. And as you might guess, that would be sympathetic output, right? Increase in norepinephrine release. And it has to be fairly dramatic. Venoconstriction is it's not a general occurrence. Happens when blood pressure falls fairly dramatically, right? To get that increased venous return to solve the problem here, get our blood pressure back up. And then, of course, our vasoconstriction, vasodilation over here. Well, again, we'll talk about hormones that do that and neurotransmitters, right? But of course, vasoconstriction, neural vasoconstriction is largely adrenergic, which would mean norepinephrine, right? Hormonally, it would be epinephrine plus other hormones like angiotensin II and vasopressin, things like that we'll talk about when we get to the renal section. All right, and there you have it. Blood pressure, a little bit about blood pressure control.